Okay, so that's all I want to say about the principle of relativity. So next I'm going to talk about the second postulate, the constant speed of light. So what does that mean? Okay, so again we can talk about it in terms of experiments. Any experiment to measure speed of light in a vacuum will always give the same result which is C, regardless of the observer velocity. So more specifically, I can describe this principle like this. No matter who's doing the experiment to measure the speed of light, you'll always get the same speed, okay? Regardless of who is doing the experiment and their velocity, provided you do the experiment correctly, of course. Okay, now note that this principle immediately explains the result of the Michelson-Morley experiment, right? Because the Michelson-Morley experiment basically was measuring the difference in the speed of light in different directions, right? But according to this postulate, the speed of light is always the same. So there's no difference in the speed of light between different directions, right? So therefore, the Michelson-Morley experiment will always give you a 0. No difference. Okay. So immediately it explains the Michelson-Morley experiment. It also explains the aberration experiment because this picture here, this one, is just a picture in the rest frame of the star. Okay? So I can take my observer to be someone who is stationary relative to the star. He will measure the constant speed of light c, so therefore he will see exactly this picture. Okay? So this principle can explain both the aberration experiments and the null result of the Michelson-Morley experiment. Okay. Okay. However, there are a few issues with it which I want to talk about now. Okay. So the first thing we have to specify is what is meant by an inertial observer. Okay. And inertial observer, the meaning in special relativity and general relativity is a bit different. In special relativity, it simply means an observer with a constant velocity. So any observer with a constant velocity in special relativity is described as an inertial observer. So there's quite an important point to be made here. Suppose that we were in space and I've got a couple of observers who are riding on rockets. Okay, here's the first one. Here's the second one. Okay, and they're moving relative to each other. Okay, so you don't actually stand outside the rocket anyway. The concept of stationary has no absolute meaning. Okay? So when you ask who is stationary and who is moving, you can't answer that question, right? This guy is moving relative to that guy, and this guy is moving relative to that guy. Okay? So this concept of stationary is a relative concept. Right? It's different according to who you ask. Okay? But if you ask the question of who is accelerating, let's suppose that there is not just a different velocity between these, but there's a different acceleration between them, okay? Which means that the distance between them as a function of time has a non-zero second derivative, right? So they're accelerating with respect to each other. Then the question of who is accelerating, that is an absolute thing. Okay? The question of who is moving and who is stationary is a relative thing. It doesn't matter. It depends on who you ask. But the question of who is accelerating, that's an absolute. The reason being in order to accelerate, you need to do something physical, right? In order to accelerate, your rocket needs to fire. Okay? And if the rocket is firing, then you feel the acceleration, right? You feel, if you're sitting in a chair, you feel the chair pushing you on the back, right? So therefore, there's a very important difference between these two concepts. The concept of stationary is completely relative, right? I can only say what it means to be stationary relative to me, right? Relative to me, this desk is stationary. That's the only sense you can say it. But the sense of accelerating is an absolute sense, right? I can say whether something is accelerating or not without reference to a particular observer, okay? Because the acceleration produces some physical effect, which you can measure. Okay? And this means, the reason I'm saying this now, this means that this definition of inertial observer is a well-defined definition, okay? Because an inertial observer is an observer with zero acceleration. And the concept of acceleration is an absolute concept. Okay? So this is a well-defined definition. Okay. And now I come to a very important point, which is a good point to finish this class on. This principle of the constant speed of light is actually incompatible with the Galilean transformation of velocities. The two things cannot be put together in a consistent way. Okay, the postulate, I'll just say postulate 2 to save writing. It's incompatible the Galilean transformation. Okay, the reason it's incompatible is quite simple to explain. Suppose that I'm doing an experiment to measure the speed of light, so I've got a light beam going along here, okay, and I want to measure its speed. Then suppose that I have one observer here, call him S, who measures the speed of light. Okay? So he's doing an experiment to measure the speed of this light beam, and he, according to the postulate, must measure the speed c. The postulate says you always measure the speed c. Okay? So this is an observer doing an experiment to measure the speed of light. Now suppose I've got a second observer here, who I'll call S prime, who is measuring the speed of light of the same beam, but the second observer is moving, okay, with a speed u in this direction. Right? So both observers are measuring the speed of the same beam of light. Then, according to the postulate number 2, this observer must also measure a speed c. Right? Because it doesn't matter upon the observer velocity. So every observer must measure the speed c. But, according to the Galilean transformation, this second observer should measure a speed c minus u. Right? But they can't both be right. Right? So either the speed of light here is c or it's c minus u. It can't be both. Right? So therefore, this principle of the constant speed of light is incompatible with the Galilean transformation. Okay? So last time we wrote down what the Galilean transformation was, specifically, and it's this. X prime, that's the position of coordinates of this guy, is equal to the position coordinates of the first guy minus the relative velocity times the time. Okay, and the time measured by the second guy is the same as the time measured by the first time. Okay? So, if the postulates of special relativity are true, then this is false. Okay? So the measurements of space and time by different observers do not transform like this. Okay? Okay, and this has some important consequences. So first of all, if the measurements of space and time do not obey these equations, then what equations do they obey? Right? So the first thing we need to do is find new equations for this kind of transformation. And the second point is that if we do make new equations, then there's no guarantee that Newtonian mechanics will still be compatible with the principle of relativity. Because when I proved that conservation of momentum is compatible with the principle of relativity, I did it using the Galilean transformation. Right? We made use of the Galilean transformation. So if the Galilean transformation is wrong, then there's no guarantee that Newton's laws are still compatible with the principle of relativity. And in fact, it turns out that they are not. Okay? So this is the reason that special relativity is so important, because it shows that Newton's laws must be wrong. Okay? Until that point in time, everyone thought Newton's laws were the correct laws of the universe, but this says they cannot be because they cannot be compatible with these two principles here. Okay. So let me just write that. So that's all we can say so far. They might not be compatible with the principle of relativity, but we'll see in a couple of weeks, actually, they are definitely not compatible with the principle of relativity. They are not. So, and therefore, we need to modify Newton's laws. Okay? This means that Newton's laws need to be changed. So this is basically a summary of the whole of the rest of the section on special relativity, which will take about the next 4 weeks. Okay? So Einstein, through these postulates, was able to explain the experimental results about the speed of light without using an ether. But as a consequence of this, we need to change the transformations of space and time between different observers. So different observers' measurements of space and time are different, not this. Okay? And secondly, as a consequence of that, we will need to modify Newton's laws. Okay? So we need to find new definitions of things like momentum and energy and so on. Okay? So that's going to be basically, like I say, the next 4 weeks. So we'll spend a couple of weeks looking at this, what the new transformations should look like and how we work them out, and a couple of weeks looking at this, how do we need to change Newton's laws to make them compatible with the principles of special relativity. And incidentally, this is where the famous equation E equals mc squared, right? You all know this equation. This one, right? This comes out of here. Making Newton's laws compatible with the principles of relativity gives you this equation. And we'll see how that comes about in a couple of weeks.